silence your phones. So we have Oded Schwartz from Berlin, as I was asking him. Graduated from Tel Aviv and is now a postdoc in Berlin. And I just wanted to say for all of you computer scientists, there should be a really good talk this member seminar at 2 o'clock by Unraveled on, I guess, on the Riemann hypothesis. He's a good speaker, he's a good expositor, so I hope it will be understandable. Okay, Oded.
Okay, thank you for inviting me. And today I'm going to talk about joint work with Gray Ballard and Jim Demel from Berkeley and Olga Holz, which I guess you all know, from Berkeley and Berlin and now here. So I'm going to talk today about communication avoiding algorithms and lower bounds for those algorithms. Considering the audience, I'll concentrate on the lower bounds and the connection between those lower bounds and expanding graphs. So communication in algorithms. So when we measure the time of an algorithm, we can split it into two types of, well, arithmetic operation and communication. And by communication, what we mean is either when we have parallel computer, that's the communication between the computing entities, be it processors or multi-cores on a single processor and so on. Here I'll always refer it as processors. And the other type of communication is communication between various types of memories. So we have, say, very fast and small memory, RAM or cache, and we have large and slow memory. And typically in an algorithm, the time spent on the communication is actually much larger than the time spent on the arithmetic computation. So this calls for finding algorithms which avoid communication as much as possible. And also, each communication operation costs more in energy terms than any flop or arithmetic operation. So this is another motivation for saving communication. So we're looking for algorithm that saves communication as much as possible, and we want to find lower bounds, say, for this problem or for this type of algorithmic class, we cannot do better than so and so. Now, this, I hope, is the only engineering-oriented slide in this talk. So here what we see is from report from 2004, the rate of improvement of arithmetic performance and memory communication performance. So this axis is the megabits per second of processing, and this is the time. And what we can see is the annual or the average annual improvement of arithmetic speed up is much larger than that of the communication speed up. And here I only considered memory, one type of memory, but you can see the same thing in other types of memory and in the usual communication in parallel computing. So this means that it is most likely that communication avoiding algorithm will be needed more and more. The fractional time spent on communication given a specific algorithm will only increase as hardware develops. Okay, so let me now formally define the three models we're going to talk about today. The first one is the sequential model, where we have fast and small memory and large and slow memory. Computation can be performed only on operands that are in the fast memory, and the objective is to minimize the communication between those. And this is the hierarchical memory sequential model. maybe a more realistic model. So here we have more than one type of memory, maybe L1 cache, L2 cache, RAM, hard drive, and so on. And we want to minimize communication simultaneously between each two consecutive levels of memory.
This is similar to this model from the 90s, near Rajavan, these guys. There was a hierarchical memory model, and they were looking for similar things. So it's
Could be, and I don't know.
you don't know.
Yeah.
Oh,
Yeah.
The costs were more specific. You're right. I don't think he's assuming any particular cost.
Yes. So here we want to state the communication upper and lower bounds as a function of the input size and the parameters of the memory levels. So their sizes and their speeds.
So the input is bigger than the memory?
So the input, well, it has to be to reside in to be smaller than the largest memory device, but certainly, typically, it is much larger than any of the intermediate levels.
So you don't consider a case where the input is small, but you need more space than the input side or something?
No, not that. All the problem we'll see today by now have in-place algorithm. So there's no problem of, yeah. Okay. Again, referring to what you said, we typically are more satisfied with cache-oblivious algorithms. That is, algorithms that perform optimally regardless of the parameters of the actual machine. So I don't have to know in advance what are the sizes and the speeds of each of the levels. The algorithm will do the best that is possible. And the third last model is the parallel model, where we have several parallel processors. Each has memory of size m. In this model, I assume all memories are the same size. And I usually ignore the topology of the underlying network connecting the processors. So I want to minimize the communication performed between the processors. And if two words or bits are communicated simultaneously, I count them as one. So let's start with a simple example. That is a matrix multiplication, the classical cubic algorithm for matrix multiplication. So how can we avoid communication here? What we can do is compute blockwise. So split the three matrices into blocks of size about square root of m by square root of m, where m is the memory size, so that three blocks fit into the memory. And now do the multiplication blockwise, where at each step we read a block of A, a block of B, do the multiplication, and update the accumulated sum into a block of C. So this gives us a communication lower bound of, well, n over the square root of m to the third. An upper bound, sorry, yeah. So, and there is an equivalent or parallel algorithm that does the same in the parallel model. So the number of actual computation has to be performed in each processor is n to the 3 over the number of processors, p. And so it manages to do, well, the equivalent to here, the same bound, upper bound divided by p. And Frigolizarson, Prokop, and Ramachandran managed to generalize this upper bound, this algorithm, to a cache-oblivious algorithm with the same performance, so that it fits any hierarchical memory model. Now the question is, can we improve these bounds for either of the models? And the answer is no. So Hong and Kang and then Ironi, Toledo, and Tiskin using another method prove that any classical cubic algorithm for matrix multiplication cannot be performed with the communication less than order of n cubed over square root of n.
What does that mean?
All right, so this is strange at first glance indeed, because I'm saying, given an algorithm, you cannot do better, but you gave me the algorithm, so what do you mean? The thing is that given an algorithm, there may be many ways to implement it regarding to how do you treat the memory. When do you do which operation? You have the freedom to perform the flops.
What don't you have the freedom to not do? So
Sorry?
what if you throw it out and use the fast matrix multiplier?
I'll get to the fast matrix multiplication in a few slides. Yeah.
How do you define the model so you can't just do that?
So you have to do all the computations.
You have to
of the
do
classical
all the
model.
inner products. In a cubic algorithm, you just have to do all the
You
n
can't
cube
use
inner.
you can't use the fact that you have the associative rule or distributive rule, or which
Yeah, I think you have to do all the pairwise inner product.
And
All
when you
the
do the
pairwise
product,
product.
and when
Exactly.
you do the product, these things have to
There are
be in
just n
memory.
cube products, and you have to
so
do
you
them
think
all.
of it as it's not really a lower bound on matrix multiply, it's a lower bound on computing the outer product of two vectors.
Yeah.
Exactly, on class of, and this may look trivial, but apparently it took many years to obtain this lower bound. So there were many implementations, and yep.
So you said that you can't know the size, it's oblivious, you don't know the size of the cache. Is it the size of the different levels?
Yeah, when we say oblivious algorithm, that means that we don't know the size of the cache or the speed, and we want still that to minimize communication. Yep.
Would it be interesting to prove lower bounds even if you know the size of the cache, or is it?
The lower bound is when you know the size of it.
Yeah.
Oh,
So
this one is when you know the size.
So the lower bound is in both cases you assume what is harder to prove. All right. So in the upper bound you assume you don't know the cache size. In the lower bounds you assume you do know them, and still it doesn't assist you.
I got that from
Yeah.
Yeah, anyway, the trivial lower bound would be something over m, the number of operations
Right.
over m, and that's a better.
Yeah. And the technique of Ironi, Toledo, and Tiskin also allows, so it also holds for the parallel case. So in that sense, the classical cubic matrix multiplication case is done, is tight. So what we do is we, sorry.
Just wondering, doesn't the parallel lower bound follow from the sequential one? Can't you simulate always with a slow up of p? Any parallel machine by a sequential machine?
Yes, but then you want the lower bound to depend on p.
Yeah,
So you care about this p factor.
No, of course.
Yeah.
I'm just asking whether a parallel machine with respect to bandwidth cannot be simulated by a sequential one with a slowdown of p.
You have to store the
Yeah, I'm just asking, so it's not.
Yeah, it's not obvious. Yeah.
So if it was true, then it would
Yeah.
follow,
No, but how would it follow? Because it slowdown of
So
If you could do it much faster than this, then you could do
So-
you simulate.
If you have a simulation,
then you say
depends
the
on the
factor of p,
parameters of the
you
simulation.
multiply by a factor
presumed
p, you get
simulation.
nothing.
No, you get. But if you could do, I'm just saying something trivial.
Could do
Right.
this with
You-
memory
you-
m, then you could do that with memory p times m.
yeah, at least the
But still,
Suppose we are talking about time and not bandwidth. Time, we know
Oh,
that
okay.
P processors cannot speed up anything by factor more than P. So
Yes.
lower bound on,
sorry, maybe I'm not reading the formula correctly.
Mhm.
that's
Is
the
it
P is not
P
square,
and
it's
M?
square rooted.
Is p and m separate variables, or are
Yes.
they the combined one variable?
No, there are two separate variables.
Mhm.
P is the number of
okay.
processors and M is the size of the
Sorry,
memory.
I thought it was just like parallel machines.
Yeah.
Okay.
All right, so this is what we did the last year. So we generalized the lower bounds of matrix multiplication to many other linear algebra or direct linear algebra operators, including, well, some people say all linear algebra. Well, most of the things that you can name, then we can show lower bounds for them, including the basic linear algebra operations, LU, Koleski, and LDL transpose, factorization, QR factorization, and many other problems. Unlike the previous known lower bounds, our lower bounds also hold for sparse matrices. So when you do sparse linear algebra, you want your algorithm to, well, you want your communication to depend on the actual number of flops you perform, which may be significantly smaller than in the case of the dense linear algebra. It holds for sequential, hierarchical, and parallel models, for bandwidth and latency. So latency means we usually don't send one bit of communication. We send a message, a package of bits or words. So, so when you optimize, you want to optimize not just the number of bits you send, but also that you want to be sure that you are able to pack them together efficiently. The lower bound holds for composition of linear algebra operations and for certain graph-related optimization problems. And recently, we also showed that it applies for fast matrix multiplication algorithm. And this will be the main thing I'll talk about today. Yep.
Again, you're assuming that you have a sort of overall algorithm for these problems?
Yes.
And just proving a lower bound on implementations of the algorithm?
Exactly. Yeah.
Not.
Exactly. Oh, so on one hand, this is sort of weak because I'm only talking about an algorithm or a class of an algorithm. On the other hand, to my defense, I can say that there are very few general lower bounds. So lower bounds for problems rather than for an algorithm in computer science. So we have maybe for matrix multiplication, there is an n square or times log n lower bound, and there are a few, but yeah.
But one exception is communication complexity, where we have a number of strong lower bounds. So is there hope of proving absolute lower bounds in this model?
There always is a hope. Well, I don't have a good answer for that now. Okay, what we also do is analyze known algorithm and compare them and see which of them is optimal. And in many cases, at least the dense linear algebra, there's a tight match. Incidentally, well, when we proved the lower bound for fast matrix multiplication, it turned out to be larger than the known upper bound. And this was worrying some. So luckily for us, it turns out that there was an error or mistake in the analysis of the upper bound. All right. Also, our lower bounds then were matched by a few new algorithms, and many of the upper bounds are still open. This is particularly true for the sparse case and for sparse cases, and many of the known optimal algorithms are not yet implemented in publicly available libraries. So this is also something that should happen. Okay, I'm not going to go into details, just want to show that these are lower bounds for all these problems for dense linear algebra, and there are matching algorithms for all of them. This is not the case for the sparse linear algebra. Here's I zoom in on the Cholesky decomposition problem, and this is our lower bound, and we found optimal communication avoiding and cache oblivious algorithm. It turns out that this algorithm was previously known, but it was not known that it was optimal. So here we have a match.
So this is the sparse case or
This is the dense case, where so we thought we invented this algorithm, but it was known for 2000. But the author of this algorithm, Ahmed and Pigali, were not aware that their algorithm is optimal. Or yeah.
Oded, I guess what's confusing here is that previously n was the size of the problem, and here you're talking about sparse.
No, this is still dense.
This is still the size.
Yeah.
Oh, this is still okay.
This is still dense. Yeah.
Confused me.
And in the parallel case for dense Cholesky, this is just another example, we have almost tight results. So the upper bound is log p factor away from the lower bound. All right, and there may be happy news here soon from the algorithm perspective. So I'm going to talk about three methods of showing lower bounds for bandwidth communication. The first one is reduction. The second is geometric embedding, and the third has to do with expander and with the expansion of graphs. So here's how we prove the Cholesky case. We show a reduction from the matrix multiplication problem to the Cholesky decomposition problem, meaning that if we have now an algorithm that solves Cholesky, we can use it to solve matrix multiplication. The thing to be careful about those reductions is that you have to be very careful with the time and communication your reduction spans. It has to be very tight, so it doesn't spend more than the time and the communication of your matrix multiplication algorithm.
Are you going to explain also the Hong and Kung lower bound for matrix multiplication or not?
The wrong analysis?
To their lower bound, basically, right? To the known lower bound.
Yeah, so the mistake there was just...
No, mistake.
Sorry?
I don't think there was.
So you're talking about?
The Hong and Kung.
No, sorry.
Yeah, so
No.
you're reducing to that, right? You're reducing to
Either that or to the Ironi Toledo Tziskin. It doesn't matter, yeah.
Okay, so in this whole paper, the main model was sort of systolic arrays in the Hong and Kung. So this is a model you care about also?
Not here.
Not here. The algorithms are even simpler to perform because it's just a rigid flow of, it's a very geometric parallel machine that
Yeah.
their algorithm works on. So that's not, okay.
So this is the second technique. And so what we do here, we look on the computation performed by the algorithm and say that amongst other things, it has this type of computations. So in the case of, this is a matrix C, matrices A and B, and this is a generalization of the matrix multiplication. So in matrix multiplication, Gij is just multiplication, and Fij is summation. So assume this is the computation or part of the computation performed by the algorithm. So what we're going to do is embed it in a three-dimensional cube. So we take only the Gij arithmetic operations and assign a point in the cube for each of them. And now we look on the, so this is the Gij operation, this body with volume V. And we look on the projection on each of the three faces. And so this corresponds to the number of A elements that we have to read or have them, and the same for B and C. And now if we know the connection between the volume and the 3 projection, this can help us give a lower bound on the communication needed. So we look on a segment of the computation. We do these 3 projections. And so we know that the number of GIJK operations performed here, the number of GIJK operations performed, well, by Loomis-Whitney bound, we know that it is at most the multiplication of the 3 areas square root. And so if we perform, so if the area of these 3 is order of m, then the number of flops operation of arithmetic operation performed is at most order of m to the 3/2. The reason I choose m is that, well, in the fast memory, I may already have m arguments. And so I look on segments that uses those arguments and maybe further m other reads and writes. And so this gives the bound. Yeah, because this was to, yeah.
Okay, so how does the volume relate to the, so let's see. So you're assuming these operations can only happen.
Can I try to explain?
Okay, but let me ask, so are you assuming that the algorithm can't compute this function g unless both a variable called aik1 and a variable called bk1j are stored in the memory?
Yeah, he is assuming that.
Yeah.
Exactly like that.
Yep.
And the output location of
So
C is also.
it doesn't do any good in this model to actually write to a lower level of memory except for an output or one of these GI values?
So you have 2 options. Either your arguments are in the fast memory, and then you have m of those, or if they are not, but you want to read or write further arguments, then you have to perform a read or write operation.
So you can't like necessarily combine operations by adding 2 things together, writing over where they appeared in the.
No, so that would be a different algorithm from my perspective.
All these n-cube multiplications.
Mhm.
Let's say the GIJK
Mhm.
are all the n-cube multiplications you have to perform.
Okay.
And what he's saying by this Loomis-Whitney is if you have m things in storage, you can generate from them only m to the 3/2 such product.
You
So
can
this
do
is
a lot of these intermediate operations if you want. I mean, they're all accounted for in this argument. You can do various combinations and reads and writes, and you have to also, you produce your output, you could store it in fast memory, and so forth. You can even lose things, you don't have to write necessarily. This is also possible.
Mhm.
You can lose you can compute unnecessarily. That's also part of it. So potentially,
Right.
your algorithm is doing crazy things. It's also accounted for.
Okay, but so I'm just trying to understand them. But then the second thing I don't understand is, in general, you can compute. I see. It's that the things have exactly this form.
Yep.
The same form as matrix multiply.
Exactly.
That you're using to get
Mhm.
this. Because if you just have an arbitrary set of triples that you have to compute. There's no reason
that would be
why
harder
you
to
can
embed.
get to
Yeah.
3/2.
Mm-hmm. Mm-hmm. So this is, we split the computation into segments where in each segment we perform at most m reads and writes, and we want to upper bound the GIJK flops, arithmetic operations. So there may be the F operations, which we don't care about, only about the GIJK, the gray ones. And so combined together, so each segment contributes m, at most m, or at least m reads and writes, and the question is how many segments do we have to have? And this is just the number of GIJK operations divided by the upper bound on the GIJK operation inside a single segment. And this gives the lower bound. So this immediately applies to dense and sparse matrix multiplication, both in parallel and sequential model. So in parallel model, you just look on the operation performed by a single, the processor that performs the maximum number of GIJK flops. And many other factorization. In some cases, it's not immediate to see that it fits form 1, but that's a general idea. It also fits some of the graph theoretic algorithm. But some algorithms just don't fit to this form 1, and this includes, as you noted, the fast matrix multiplication algorithm.
What do you mean sparse included? I mean, you didn't define the sparse problem. You didn't define exactly what is the sparse matrix multiplication.
This is right. So when you have sparse matrices, sometimes practically, technically, you don't store the entire matrix, the n square entries, but you just point to the entries where you have non-zero elements. And then when you perform, say, matrix multiplication, you don't have to perform the n cube operations, but just you just need to pay attention to those non-zero values. And then you have less computation performed, and now if it still fits form 1, so GIJK are the actual multiplication performed, so not including the multiplication of elements that one of the pairs is 0. We don't care about those, and then we can give lower bound that fits better the algorithm.
So this argument also fits algorithms that magically know what to do and what not to do, right? So if there is a 0, the algorithm may already have the knowledge, quote unquote, that there is no need to perform anything, and therefore this will not be accounted for in its GIJK count.
All right, so let me now talk about the lower bound for fast matrix multiplication, and this will include the idea of expanders. So just to remind you, when we perform, how do we perform fast matrix multiplication? Let's start with the Strassen algorithm. So what Strassen noted is that if you know how to multiply 2 by 2 matrices with 7 instead of 8 multiplication, then you can use that recursively, and you can use that recursively and obtain a running time which depends on the number of actual multiplication you perform. So here it's instead of n to the cube, you get n to the omega, where omega is log 2 of 7 instead of log 2 of 8. And well, using the same method, you can divide. You can start with, instead of 2 by 2, start with n0 by n0 matrix multiplication. And if you can do that using few multiplication, then you similarly obtain fast matrix multiplication. And there was a long list of improvements to the best known today, Coppersmith and Winograd omega, which is about 2 to the 2.38, and this was later repeated using other approach, using a group theoretic approach. So what we want to have is a lower bound that somehow fits all these algorithms. I'll demonstrate it only on the Strassen case. What is the communication bandwidth of Strassen? Well, what we can do is, as in the classical case, work kind of blockwise. So do the recursion as usual, but once we get to blocks, that submatrices that are sufficiently small to fit into memory, do everything in place, not waste any more communication. So this gives communication bandwidth of, well, here it's n over square root of m to omega, So this is the number of flops of block operation, and for each block operation we need to read 2 blocks and write a block, and this is order of M communication. So this is the -1 here. Okay, this is clear. Right. So as you ask, it's not straightforward, or it's not clear how one can do the Strassen algorithm in place, but so we know how to do that, but even if we didn't, we could, once we got to this size, just perform the classical algorithm. And so that is trivial to do in place. So the question is, can one improve that? And the answer is no. We show a communication lower bound of, well, tight. Up to a constant factor, this bandwidth cannot be improved. Yes?
Can you again explain what you mean by the Strassen algorithm? So what are you allowed to compute? Do you have to compute the products of the linear forms that appear in Strassen's algorithm?
Yes.
You have to,
so you have
to produce all these products.
Yeah. Mm-hmm. So you have to actually do all those. You have the choice of deciding.
Those are just what happens when you unravel the recursion.
Yes. That's, yeah.
So not those, but
Yeah.
what happens.
What practically happened? Okay, let me. Yes. So I'll unravel them in a minute. Okay, and so we conjecture that the same technique works for the for arbitrary fast matrix multiplication. And here's how we're gonna prove in general. So we look on the computation graph. So here we have a vertex for each argument. The blue ones correspond to inputs and outputs, and the black ones are intermediate values. And we have edges, directed edges, connecting them according to dependency. So if this is the result of the multiplication or summation of those two, then we have 2 edges going inside here. Now what we do is we partition this graph to segments, and you can think of those segments as flops or arithmetic performed in the various processors, or you can think of them as operation performs in a given window time in the sequential model. Now, if we can show that each such segment of the graph has many edges going into and out, inside and outside of it, then this means that this segment has to communicate a lot. Yep.
Can you formulate this model as a graph pebbling model?
As a?
Graph pebbling game. The standard kind of way of proving time-space trade-offs. So you have M pebbles that you can place on the nodes of your DAG. And when you have you're allowed to pebble only a node where you have you've covered the incoming nodes, all the incoming edges. And then you can place a pebble on the node, and you can remove pebbles when you want to.
Yeah. So what you're suggesting is potentially stronger than what we do here, because it somehow takes into consideration the synchronization. So you cannot do specific advance on the graph before you're done with this one. And here we don't assume that. So potentially, maybe for some problem you could get better lower bounds with what you suggest.
In your model, you have to. I mean, there are pebbling models that it's not the standard pebbling model doesn't take this into account. There are pebbling models. You have to have pebbles here of 2 kinds. Pebbles that are in a limited number that is in the main memory, and that is the fast memory, In an unlimited, there is the
Number
main
that are
memory.
in slow memory. Right. Okay.
And you can exchange,
Oh,
but it's an operation.
Yeah.
One to the other, but that's an operation.
Okay.
So you divide the graph to these segments, and you want to show that every segment has what?
So if we look at a specific segment, so these are the edges that leave the segment. This means that all these vertices have to be, or all these values have to be written to the slow memory or communicate to other processor in the parallel model. And these are all vertices that have edges going into them. So, or these are all vertices that are read by that segment. So this and this gives you the amount of communication you have to perform. So if, for example, if we assume that for some magical reason the graph is regular or bounded, constantly bounded, has a constant bounded degree, then the number of edges connecting S to the rest of the graph is proportional to the number of reads and writes that has to be performed. Okay. So this is the Strassen algorithm, unraveled. So these are the A and B elements. What happens in Strassen, we do encoding of the elements of A, so some weighted sums of the elements of A, and the same for B. Then we perform pairs of multiplication of pairs of element, one from A and one from B. And this gives us the encoding of C, and then we perform decoding of these into the actual output C. So again, weighted sums. So let's be now specific. So you can either check or believe me that this corresponds to the computation graph of Strassen algorithm for 2x2 matrices. And incidentally, these three graphs, the encoding of A and encoding of B, these two graphs are isomorphic, and they are, well, almost isomorphic to the decoding of C, except that here there are missing two vertices. There's just a copy. But if we reorder the vertices, you can see that these three are identical. And now, so this corresponds to the, but I see that now that I'm running out of time. So.
Wait a minute, you started, you have 15 minutes.
Oh, 15 more minutes. No, that would be great. Okay.
And then you have another 15 minutes before it's conventional.
Yeah, we start with 15 minutes and then we evolve more.
All right. Okay, so let's think of what happens when we do one recursive step. So we so each element is actually a 2x2 matrix. So we replace each vertex with 4 vertices. The connectivity remains as before. So if that vertex was connected to that vertex, so the first one is connected to the first one, the second one to the second one, and so on. And now multiplication of two blocks is performed as in the previous case by using the previous graph. Now let's concentrate on the decoding C part. So when we perform one further step of recursion, we split each vertex to 4. This is like taking 4 copies of the same graph. Then we need another level of encoding or decoding in this case. So this is another level of the C1, of the encoding for 2x2 matrices. So now we need to claim something about the expansion of this graph. If we can show that this graph expands well, then this means that we have a lower bound for the communication of that algorithm. We can do that in two general ways. One is combinatorially, just show it by hands. And the other one is using spectral analysis. And we can, from now on, we can ignore the direction of edges. This will make the analysis easier. Also, we don't care whether we're talking about reads or writes, so it's fine. And we allow ourselves to add loops for the graph. This doesn't change the actual communication.
You are just proving the expansion of the, but for in general, you were interested in expansion of sets of about square root the size, but right? But you will prove expansion
So
for all sets.
yes. So this will be the next slide. So just to remind you, relative edge expansion H, well, we look on subset of size at most half, and we ask how many edges connect them to the rest of the graph. And so this should be S. So we look on the edges connecting S and the rest of the graph and divide it by the number of edge endings touching S. And we look on the minimum over all such sets. This is the edge expansion. And we can define spectral expansion. So that's looking on the eigenvalues of the graph and comparing or looking on the gap between the large one and the second largest one. And that's the spectral gap gamma. And we know that there's a connection, so the edge relative expansion is at least half the spectral gap. And also there's an upper bound. So this should answer your question. How do we prove the expansion of the graph? So we break the graph into subgraph, edge disjoint, but not necessarily vertex disjoint subgraph, where each such subgraph corresponds to multiplication of square root m by square root m matrices. And given a set S, we look on the expansion of S in each of those subgraphs. And we just sum them up. So the number of edges from S to the rest of the graph, well, it's just do the same in each of the composing subgraphs. Now, this is lower bounded by the relative edge expansion of each of the graphs times the size of the subset of S in that graph. But all those graphs are actually isomorphic, so this is the relative edge expansion of each of those graphs times, well, those S's may actually intersect, so the sum of those S's is at least the size of S. Yes?
So what if S is more than half of the nodes in some of the regions?
What if?
When you divide the graph up into regions,
Yeah.
S contains more than half the nodes in the region.
It doesn't matter. It's between the set and its complement. So one of them is less than a half.
No, but the one in the region.
Yeah.
No, but it's counting just the number of edges between SI and the complement. Of
Yes.
the
So this is one thing we could do, but this is not what we actually do. So what we eventually we are not interested in arbitrary set that expands. If you remember, we divide the computation into segments of given size. So we just have to make sure that that given size is at most half the size of the graph. So this is in our hands to control.
Okay.
Yeah. And so what we get is that the total bandwidth is lower bounded by the number of vertices, which is the running time of the algorithm, times the relative edge expansion of the same graph, but of smaller size, the graph that corresponds to small matrices. And by the previous expander theorem, we can do the same, but with spectral gap instead of edge expansion. So here I'm being specific on what we want to show in order to get optimal lower bounds. So we need to show that a set of about this size, so then the running time corresponding to square root of m by square root of m multiplication, expands, well, to order of m sort of reads and writes. And to do that, this means that what we need to show is that for every n, the expansion of the graph is omega of n squared over n to the omega, or 4 over 7 to the log of n.
It's not really expansion, it's shrinks.
Yes. Yes. So yeah, this is what I want to say. So is it a good expander? The answer is no. So this computation graph are actually very bad expanders, but they are just exactly good enough expanders to give us the lower bound we want. Okay, so let me quickly say how we actually prove that combinatorially or spectrally. So if we want to show that combinatorially, okay, Rico, this is the decoding of C graph, and this is the lowest level. So these are decoding of C1 graphs, and this is the rest. Now, what we observe is that we can think of each of the decoding C graphs as a consistency gadget. So green corresponds to a decoding C graph where all vertices are in S. White is when all vertices are not in S, and red when that is mixed. So if it is mixed, then there is at least one edge connecting a vertex in S to a vertex outside S. So this means a payment in the bandwidth or in the expansion. So either there are lots of reds, and then we are done, we are happy. We pay a lot in the expansion, or almost all of them are either entirely green or entirely white, or either entirely in S or entirely not in S, in which case the fraction of S vertices on the bottom level is exactly or almost exactly the fraction of S vertices here in the first level of the rest of the graph, of each of the four parts of the rest of the graph. I'm not sure I was clear here. So let me go one step backwards. When we
just to make sure, these are the multiplication part. So the left side of
yes.
the graph is the multiplication, and
so
afterwards is the linear operation.
Exactly. Exactly. And so let me remind you, when you do one step of the recursion, what we do is we duplicate the graph four times, and then connect them crosswise with graphs corresponding to the basic, the 2x2 case. So either there are lots of red, there are lots of mixed in S and outside S elements here, and then we already pay a lot, or they are almost all trivial. That is either completely in S or completely outside S, in which case the fraction of S vertices on the bottommost level is exactly the fraction of S vertices in the next level, but even further, those four graphs, if you look on the bottommost level, they have almost exactly the same fraction of S vertices. So either you pay a lot, or you remain with the same case, but contracted by 4 to 7 ratio. And you do this contraction over and over again until you get to a size which is order of m. So you have the same fraction of S vertices here as you have here, and this gives you exactly what you want. So this is one approach. And the other approach uses the zigzag, the analysis used in the zigzag construction. and this was later used in the proof of the PCP, the proof of SL equals L, the quantum explicit quantum expander construction, and the Ramanujan zigzag construction, and probably in many other places. So we use the same analysis. The only thing is that there's one thing that is a bit trickier, because the replacement product here is not uniform. For some vertices, you just duplicate them. Some vertices, you duplicate them and install a graph on them. This is unlike what happens in the zigzag product, where you duplicate the graph, you duplicate each vertex, and you install on all the copies of the vertices the same graph. But other than that, it's almost identical. So again, we look on the same graph, which was duplicated 4 times and then connected with cross-connecting small graphs. And what we do is we look on arbitrary vector, and we want to show that, well, if it's perpendicular to the stationary distribution, then it shrinks. How much it shrinks? Exactly this thing. This is what we want to show. And this should be done in a very similar fashion to what is done in the zigzag analysis. So either it shrinks in both sides, in which case we're very happy, or it shrinks on one side, at least one side. And the thing is, if it shrinks on one side, then on the other side it has to be stationary. So, for example, if it shrinks on this side, then this means it is stationary here. So there is a significant weight on these joint vertices, a constant weight on the joint vertices, and so the induction hypothesis for this side of the graph is sufficient to prove what we want. On the other case, if it shrinks on this side, so it is stationary on that side. Here we have many vertices, so maybe the weight here is very small. Still, the contraction of this side of the graph is sufficiently strong to give us what we want.
So there's probably a general statement, like so you mentioned other recursive algorithms that you can handle also. So there's probably a general statement about the somewhat different product and replacement, the one that arises in this recursive algorithm, for which you can bound either the spectral gap or the edge expansion.
Yeah. But at this point, the only thing we know, we wrote how to prove how to bound is Strass and case, but indeed it seems that this is more general and can be used for many other types of algorithms. So we showed lower bound using either reduction, either using Loomis-Whitney, and using spectral analysis for many types of algorithms, but some of them have tight upper bounds. Many of the sparse cases don't have upper bounds. So this is one thing that should be done.
What about if you know the graph, if you know the matrix ahead of time for the sparse case? So you know the zero, you know the structure of the matrix ahead of time.
Yes, this is.
Would you have better algorithm?
I think this is what you assume, that you are given. What do you mean by no?
I assumed it for the lower bound.
But also for the upper bound. This is what you're given. You're given the non-zero. So you're given, for each vertex, you're given a list of. All right.
Let's say you can design, it doesn't cost you to design the algorithm, but the best algorithm for the given matrix.
So you're saying you want an algorithm that multiply matrices, pair of matrices with given a set of non-zero. Yeah, I don't know. Yeah, so as you said, we would like to generalize the spectral approach to a wider class of algorithm, and potentially this could also serve as a algorithmic approach. So if you know the structure of the computational graph, maybe you can look for sparse or small cuts or small mean uncuts or multi-cuts in the graph that would split the graph so you can compute it in parallel with very little potentially optimal communication. And maybe the most basic thing is to show communication lower bound to a problem rather than to a specific class of algorithm. And of course, modern computers are more complex than the three models I talked about. And so it would be very interesting to formulate more general model with multiple level of hierarchy level of parallelism mixed with all kinds of memory solutions to be able to argue systematically about such system. For example, we know that the simplest straightforward recursion approach usually is usually cache oblivious for the multi-hierarchical level of memories. But there's no such general technique for parallel models. So it would be very nice to have something like this. Yep.
I wanted to ask about GPUs. So how well does this work capture GPUs?
So our model doesn't. So GPU is graphical processing unit, and it has the property that it performs arithmetic computation very fast, but its communication ability are, well, limited. So
is it clear that it's by design or by that it's physically limited, or it's the programming model?
No, it's economic reasoning. So also the reason that memory develops slower than CPUs is not anything physical. It's just apparently the market demand.
So the question was whether the GPU manufacturers are not as open as the Intel, etc.
Mm-hmm.
They don't give you they give you a certain programming model for the GPU, but it doesn't necessarily correspond to their actual.
Yeah.
So the question is whether the limited communication is really inherent in the construction of the GPU.
Yeah, I actually don't know. Yeah.
If you could prove a lower bound for a problem, would that also prove a time-space trade-off for the problem in traditional models? So like, can you simulate? I mean, it would seem like it would, right?
Yeah. The space is M always in this
Right.
lower bound. So it seems to me, yes. No.
So that's one reason. I mean, we have barely superlinear time-space trade-offs in general models.
Mm-hmm.
But on those M inputs, you can perform an intractable operation. So that's you read.
Yeah.
So in a way, there is a trade-off here because so the communication lower bound we obtain depends on the expansion of the graph. So in order to make fast matrix multiplication faster, what we actually do is we do the encoding and the decoding better mixing, or so in one sense we improve the running time, but on the other hand we increase the local communication. So maybe this is one way to see that.
The question is, what does a result like ICA is lower
Mm-hmm.
bound?
Yeah. But
What does it imply here?
okay, so saying the full so it's not clear that the best algorithm in this model is, so you have this kind of notion of you have a sequential algorithm and then you make it an algorithm in the model, and what's the best way of translating? It isn't clear that the best way of solving the problem directly in the model corresponds to any sequential algorithm.
Right. No, but like the result like on branch improvements,
Yeah.
Mhm.
where the bandwidth, where the length of each layer is 2 to the m,
Mhm.
that corresponds to the model.
Yeah.
Okay. Well, that doesn't allow you to write to slow memory.
It does,
How
because
how do you simulate that?
oh right, it doesn't. You do not.
So it's a strong. You would need a stronger lower bound than the standard. So I think that's one reason why this is at least an alibi for you. You can say to do this would also solve. You would have to solve this classical problem in complexity theory plus add this following power.
Yeah.
Do it even when you add the following power to the model.
Yeah.
I guess we went into the question mode, so more questions. So, it seems that what you are proving, and it seems that I'm talking about the last part, it's sort of in the spirit of Valiant. Valiant was trying to prove lower bounds on computations, and he observed that when you compute let's say the Fourier transform or something like that, then whatever computation you use, if it's linear, it must be a super concentrator.
Mhm.
And what you are saying here is now you're looking at matrix multiplication, let's say fast Strassen matrix multiplication, you say no matter how you are using it, how you are, how the computation graph looks like, it has to be a somewhat decent expander. In fact, it seems that the expansions improves as omega decreases.
Exactly.
If your result generalizes to all algorithms, and when omega equals 2, then you really show that the computation graph must be a real expander, right? Because
Yes. Mhm. Mhm.
I remember the formula. It's omega over 2,
Yeah.
right?
Oh.
And you get m, so
Yeah.
that's have linear number.
Right.
Right. So maybe that's a way to rule out this
To rule-
recursive type.
Strassen-like algorithm.
Maybe this. I don't know how, but
Yeah.
Maybe it's an explanation why Strassen's algorithm worked well and others didn't work
what do you mean? It works well.
in practice.
No, I'm talking theoretically. It seems like if you had a Strassen-like algorithm which achieved omega equals 2, like the Ullmans and these guys.
So it has to be a very good expander.
Then the graph that would result, the computation graph, would actually be an expander. Because the limitation.
Then it would be right. Then it would work, and then it would take it longer to process. So it wouldn't be better than the.
Longer in practice. You mean that it would be faster in theory, but you'll suffer a lot from the communication. Yeah.
Yeah. Oh, you went talking about the.
So fast matrix multiplication is slow.
There's a lot of
Yeah.
more questions. Thank you.
Thank you. זה היה מספיק תיאורטי?
כן, לא, זה בהחלט היה מספיק תיאורטי. אני חושב שזה לא כל כך ברור ההסבר שלך, אתה צריך לחשוב איך להציג את זה אולי בצורה יותר ברורה, את הקשר בין